Next is Biot-Savart's law. So, the Biot-Savart's law is also called as the Ampere's law of the current element. So, Biot-Savart's law is also called as Ampere's law of current element. The Biot and Savart conducted an experiment on the force which is exerted by an atomic current on a nearby magnet, and they arrived at a mathematical expression which gives the magnetic field at some point in the space due to current. So they conducted experiment on the force which is exerted by an electric current on nearby magnet, and they arrived at a mathematical expression which gives the magnetic field at some point in space due to the current. So it gives the differential magnetic field intensity due to the differential current element. If we consider current I flowing in differential length of the filament DL bar, then P be the point of interest at which we have to find out the magnetic field intensity. And here the differential length of the field is so if P is the point of intersect at which we have to find out a magnetic field intensity, then the differential length of the filament is dl bar and current I passing through it. So differential current element is I dl bar, And what is theta? Theta is the angle between the filament and the line connecting directional length to the point. So theta is the angle between the filament and the line connecting a differential length to the point P. Now what is the statement of Biot-Savart's law? The magnetic field along a vertical current, a magnetic field B along a vertical current carrying conductor or wire in a closed surface is directly proportional to the current I and inversely proportional to the perpendicular distance from the point of conductor or wire. So this law states that at any point P in the differential magnetic field, the intensity produced by the differential element is proportional to the product of the current and the magnitude of differential length and sine of the angle between the filament and the line connecting differential length to the point P. So differential magnetic field intensity is inversely proportional to the square of the distance from the differential element to the point P. So this is the statement. Next is the proof of this Biot-Savart's law. So if we consider a current carrying conductor in a closed surface, then B is directly proportional to I by R, and for proportionality we keep K is proportionality constant and its value depends on a nature of closed surface where conductor is situated. So from the statement of Biot-Savart's law we can write the mathematical equation as if dH bar is proportional to the product of current I and the magnitude of differential length dl, that is dH bar is directly proportional to I dl, and dH bar is proportional to the sine of the angle between the filament and the line connecting a differential length to point P, that is dH bar is directly proportional to sine theta, and dH is inversely proportional to the square of the distance from the differential element to the point P. So dH bar is directly proportional to 1 by r square. So dH bar is directly proportional to IDL sine theta by r square. What is K? K be the constant of proportionality. dH bar is equal to K IDL sine theta by r square. So dH bar is inversely proportional to the square of the distance from the differential element to the point P. Now here mu 0 is what? Mu 0 is permeability of the free space, and K value is also given. So B is equal to mu 0 I by 2 pi R. Now if dH bar is directly proportional to 1 by r square, then we can write dH bar is directly proportional to IDL sine theta r square. So if we write K as proportionality equation is K ideal sine theta by r square, but K 1 by 4 pi value is K. Now so the Biot-Savart's law, here the magnetic field strength at any point produced by the differential current element is directly proportional to the product of the current through a differential element length of the differential element and sine of the angle between the line joining the differential element with the point and the element, and it is inversely proportional to the square of the distance between the differential element and point. So it is a vector quantity and its direction is represented by means of unit vector, we can say AR. So what is the application of this Biot-Savart's law? The expression for the magnetic field strength produced by the infinite long straight conductor, we can say rectangular system. This is the application. If we consider the current element is located at point 1 and we have to calculate the dH bar at point 2, then the equation becomes dH2 is I1 dL1 AR bar AR12 bar The unit of magnetic field intensity is what? It is ampere per meter. So this diagram shows the direction of magnetic field. In the first direction, the electric current, in both the diagram, the electric current go in upward direction, that is in the direction of the thumb, and in the first direction the magnetic field, and in both diagram the magnetic field is shown. So the magnetic field is according to our four fingers, where the direction of this is in the direction of the magnetic field is related to the fingers. So direction of the thumb denote the direction of electric current. Now what is Ampere's circuit law? The Ampere's circuit law states that the sum of the tangential component of magnetic field of induction and the length of an element of closed curve taken in magnetic field is I times the current which passes through an area. So delta BH summation of BH delta L is mu 0 I. Now what is the proof? Here the proof of the Ampere's law is given. There are different applications of the Ampere's law, like magnetic field inside a long solenoid, the magnetic field from a long straight wire, magnetic field inside a coil, and magnetic field inside a conductor. So these four diagrams shows the Ampere's law, applications. Now the main difference of bandwidth, here the main difference is bandwidth, and both the law states that so the difference is same as that of between the Coulomb's law and the Gauss's law. The Coulomb's law and Gauss's law both help us in determining the charge contribution, but the Gauss's law is easier and convenient in the sense that it uses a symmetry, for example spherical, cylindrical, cubical, etc. Similarly, Biot-Savart's law and Ampere's law both helps in finding magnetic field distribution, but Ampere's law takes a symmetry into account as its closed line integral. Both the laws can be used to calculate the net magnitude, so field produced at a given by a various distributions of the current. The situation where Ampere's law can be used is the magnetic field of solenoid and magnetic field of the toroid. So these are the two applications. Thank you.